We already mentioned consistency, but we will revisit the topic in this lesson, and to keep the discussion concrete, we will talk about consistency in the context of distributed data stores. In the previous lesson, we talked about distributed transactions and how Google Spanner, by relying on GPS and atomic clocks to implement true time, achieves linearizability and external strong consistency for its transactions. In practice, however, distributed applications operate across very diverse infrastructure, and the availability of such clocks cannot be always assumed. So for the many such scenarios, it is still important to provide correctness for how the state of the distributed application is accessed and updated, and for this, we need to ensure it is consistent. So in this lesson, we will talk about consistency. We will ground our discussion in the context of globally distributed data stores represented as key value stores, and we will illustrate these by describing Facebook's Memcache architecture. And then we will talk about several consistency models, and for this we will rely on the paper Cops Don't Settle for Eventual Consistency, which describes some of the issues with several consistency models and proposes a new model called Causal Plus consistency. We gave already an example of what can go wrong in scenarios where we don't have consistency guarantees in some of the previous lectures. Here is another illustrative example from a paper called Potential Dangers of Causal Consistency by Peter Baylis and others. So we have three distributed participants, Bob, Alice, and Carol, and they share some message board. Let's say Bob first announces Sally's sick, and then immediately afterwards he says Sally's well. Alice sees both updates and says great news. Carol, on the other hand, only sees Bob's first update and then Alice's update, so she's majorly confused. If the message board were a single centralized database, this scenario is unlikely to happen. However, in a distributed system, this is quite possible. Ensuring the correct ordering and propagation of all of these updates is hard in distributed systems because we replicate state to multiple locations in order to deal with failures or to ensure availability and responsiveness of the system, regardless of load and network partitions. In addition, we also have extensive use of caching as a technique to perform performance. So we need some guarantees on how updates to a distributed state are propagated and become visible externally to the different users of the system. We need guarantees about the ordering of the writes so that somehow great news doesn't become visible to Carol before the update Sally's well. This is clearly important, but it is made hard by the fact that we maintain multiple copies of the state and then further complicated with various forms of failures. The need for consistency, coupled with the need for performance and availability, have led to a sort of compromise. The compromise is that, we provide consistency, but we decide what type of consistency model to support. A number of consistency models exist. I should note that when we say that a system supports some consistency model, we mean that the system makes a guarantee about the ordering of the updates in the system and how these will be visible to ongoing read operations. It's like a contract with the system. We've mentioned some of these models so far. We talked about strong consistency model, which provides linearizability, and it guarantees that the real ordering of the events or the updates of the system will be visible to all. We also mentioned sequential consistency, which guarantees that a single ordering of all of the writes in the system will be seen by all of the participants, but that this ordering is not necessarily going to be one that matches the real one. Causal consistency is a model which guarantees that the ordering of the updates will be enforced only for those operations which are related with the happens before relationships. For two writes, if the second write was performed after that node read the value that was written by the first write, then these are causally related. Otherwise, they're not. If they're not causally related, there are no guarantees about their ordering and how their ordering will be perceived by different nodes in the system. Another model that is commonly used in practice in distributed web services is that of eventual consistency. This model acknowledges that it is possible to have periods where the view of the data store, the view of the data in the system, is not up to date. It is not consistent. However, as long as the partitions in the system and the failures are not permanent, it guarantees that eventually all writes will become visible. But it doesn't specify anything else. Other models have been defined as well, and if we look at all of them, we can sort of order them on an axis that has consistency on one end and availability on the other. In that sense, many of these models, they essentially trade some amount of consistency. They relax the consistency and the ordering guarantees they maintain in order to improve the availability of the distributed system. What we can conclude from that statement is that, in general, weaker consistency models provide opportunities for greater availability. There has even been some work on quantitatively analyzing the trade-off between the two, using the number of updates that may be delayed and not yet visible at a node, and then also the number of out-of-order updates that might be visible in the system, but cannot yet be committed. If you would like to read more on this topic, I recommend a paper called Cost and Limits Availability for Replicated Services, which was published a long time ago at SOSP in 2001. To make the discussion about consistency more concrete, we will talk in the context of key-value stores. Key-value stores are data stores where each piece of state in the system, the data, is uniquely identified by some key, and the value associated with that key can be some arbitrary data blob of some size. This illustration here is the simplest illustration of a key-value store, like a simple hash map. The basic operations on a key-value store are put, which writes a value for the associated key, and get, which reads or returns the value associated with a key from the data store. A key-value store can also support other operations, for instance, scan or a range query, which returns all values with keys in a given range. Additional, more powerful models may be layered above this basic key value model, depending on whether there is additional information captured in the data store, such as timestamps or about relationships among key value elements. Such systems may also support more complex operations on the data. For instance, they can support operations involving multiple keys, transactions involving multiple keys. One simple and popular key value store is Memcache. You may have heard about it or even used it, given that there is an open source version that's available, and it was officially designed and released by Facebook and was presented at the NSDI conference in 2013. Now, at Facebook, Memcache has subsequently been largely replaced by another system, Tao, which was coincidentally presented in a paper just a few months later at the Usenet ATC conference in 2013. The motivation for this new system was to have something that is much better suited for the graph-based operations. You can imagine that Facebook has a big social graph that's used to generate the newsfeed pages. It needs to be traversed to make recommendations, etc. And so there are a lot of graph traversals that have to be performed. So this new system was in a way optimized for processing on such data. However, the Memcache NSDI paper is still very interesting for us to talk about because it describes how this key value store Memcache is used in several different deployment contexts, from within a cluster to across geographically distributed data centers. And then it describes a number of different mechanisms that are used to provide consistency, and each of these mechanisms essentially realizes some trade-offs that are acceptable in the appropriate deployment context. The different contexts where Memcache is used include within a single cluster, so this would be a set of machines in a single data center. With multiple clusters, again, this would be in a single data center, but they would be grouped logically, one cluster versus another cluster. Or geographically, these can be distributed to different locations across different data centers. When we talk about clients here, this could be external clients. However, this could also be the different applications of Facebook's applications that also execute in the same data center and access the key value store to perform different operations. The storage tier here is what provides persistent storage of the data, and this could be a MySQL database or a cluster of databases across which data is somehow sharded. In this context, Memcache serves as a in-memory cache for the objects that are retrieved from storage, and hence the name Memcached. The design of Memcache as a cache for the stored data follows what's called a look-aside cache design. Let's explain how this works. So in a single cluster, many of the large-scale internet applications are very read-heavy, and the reads are served over very large data sets. Likely, however, the reads are not very uniformly distributed, and there are some items that are more popular, and we call this hotter items. It's also quite common for items to have temporal locality, and more recently added pieces of the state tend to be hotter than older ones. All of these aspects make the workload a good candidate to benefit from a smaller cache that's kept in memory. This way, these hot or recent items can be accessed from cache as opposed to accessing a much slower storage tier on some persistent devices on hard disks, for instance. Now, not all the data fits in memory, and also data needs to be persistent, so ultimately all data does need to be stored in some persistent storage. And at the time of this work, this was stored in SQL databases on hard disks. The design of Memcache makes two decisions. The first one is to use an in-memory cache that is designed in a fairly simple manner, so it can respond to queries really quickly, and it can support, therefore, a large number of requests. It can be efficient in terms of the capacity, the amount of memory that's allocated to this Memcached component, so that much more data can be ultimately stored in memory. To achieve this, Memcached is a very simple in-memory object store, and the cache components of the Memcache architecture are called Memcached. Second, unlike the caches that you're maybe used to see as part of the processor architecture or the file system, this cache does not sit in front of the database, but on the side. So this is what the look-aside cache looks like. It's called look-aside because the client application that's trying to access it will explicitly perform a GET request from this cache. If the GET is served from the cache, if it can be satisfied, then great. Otherwise, this means that the requested element is not in the cache. We have a cache miss. If we have a cache miss, in traditional caches, the request is automatically going to be routed to the lower levels of the hierarchy. But here, the miss will be returned to the client, and then the client explicitly will perform a database lookup. Note here, this database lookup is different than this GET operation. It may be a much more complex interface to the database to perform the database lookup query than the simple GET key interface that we have to the Memcache. This makes sense because in the persistent MySQL database, the data is organized very differently, so it requires a different lookup operation. Now, once the data is retrieved from the database, the client explicitly issues a set operation and then adds this value to the Memcache. This way, this cache is still filled on demand when data is accessed, and this is similar to what you see in other caching systems. So we understand how the Memcache gets populated and how values are served from it, but what happens on an update? Any update has to be reflected in the database, and we know that because the system has obligation to keep data persistent. This in-memory layer isn't persistent, and that's why we perform the database update explicitly to the database. There are multiple options on what we do with the cache data. We can mark the data in the cache invalid and delete it. We can update it with the new value. Given that the cache is a look-aside cache, if the system chose to update it, it would have to rely on these clients not to crash or to be delayed or corrupt for the update to be performed correctly. So in that sense, it could potentially have made the design of the cache more complicated. Instead, when an update needs to be performed, the Memcache client would simply delete the cached entries from the Memcache and update the database. The good thing about deletes is that they are idempotent with respect to the correctness of the database. The worst case, we'll have a lot of cache misses, and that will make the cache ineffective, but it will still make the results correct. The deleted space, the entries that are marked as deleted in the Memcache tier, they can be reused by new inserts. And also to make more space, Memcache uses a simple LRU mechanism. So the least recently used updates are essentially discarded. As you can see, the database updates are performed before these deletes, so there is no need to further write them out to the database. Just discard them. This is possible because the Memcache consists only of clean, unmodified, read-only data, essentially. This design decision is another feature that allows the Memcache tier to be as simple as possible, and because of that, to get some additional efficiencies. Now, the thing to note is that this cache is non-authoritative, so it's intended as a performance optimization. Only the database has the definite view of the system state. These semantics of the system design are actually exposed to the client applications of Memcache. So if an application really cares for some strong guarantees, it knows that it needs to directly perform the database operations and to bypass the cache. I want to point out a couple of more things. First, it is possible to have this in-memory cache give some persistence guarantees, just like the database. One straightforward way that this can be done is by backing it with persistent non-volatile memory. This is not something that's considered as a design point from the system, at least not at the time when this work was done. And another thing that I want to highlight and reiterate is that when the cache is present directly in front of the next level of the hierarchy, then in those scenarios, the cache is really not explicitly exposed to applications. The applications can perform read or get or whatever types of requests, and they would get data back from somewhere, either from the cache or from the lower level, from, let's say, the on-disk database. And because of that, in these scenarios, when the cache is, let's say, in front of the database, it has to provide to applications and to the data accesses exactly the same kinds of semantics as those associated with the database itself. By having these two tiers be explicitly separate, the caching tier versus the storage tier, in this Memcache designs, we're able to associate different guarantees with the two different tiers and therefore achieve some optimizations in the caching tier. Let's look into the mechanisms used in Memcache. Consider this scenario. Two web servers try to access the value of an entry in the database. Let's say the initial value of this element is A, and the element is not present initially in the Memcache. Each of the servers first tries reading from the cache and gets a miss, and at that point tries reading from the database. Let's say the request from web server 1 is the first one that arrives, and the database responds with the value of A. The web server Memcache client will then initiate a set message to set this value in the cache for future requests. In the meantime, the value of the database entry changes. Let's say some other process that's not shown here is going to update the value of A, and this is going to become B. Now, immediately after this happens, there is a read request from web server 2. It also has a cache miss, and it reaches the database. It receives this new value B. So it will now try to set the value in the cache to the value B, which it read. Since these two set messages are traveling over a network, it is possible that they will be reordered and that the set message from web server 2 arrives before the set message from web server 1. So if we take a look at the Memcache, its value will first become B, and then it will become A. This will leave the cache in incorrect state. The solution that Memcache uses to prevent this is to use a mechanism called leases. Leases are something you may remember from, say, the Coda paper in 6210, and this is when the system provides some guarantees, but within some time bounds. In this case, the lease is a token issued by the cache on a miss, and it provides some greater control over how it serves the read operations. For instance, it can detect concurrent write. So in that sense, it can be used in order to enforce some ordering on the writes. The paper describes in more detail other scenarios and other potential problems that can occur in Memcache, which can also be managed with the lease mechanism. For instance, for the so-called thundering herd problem, by controlling how many leases are issued at a given point of time, Memcache can control the number of accesses that will be served a token, and therefore the number of accesses that will be allowed to proceed to the database. Now, a single Memcache instance is going to have some finite capacity. It may be very large capacity if we have spent a lot of dollars on DRAM or on some of the new multi-terabyte persistent memory technologies, such as Intel's Optane persistent memory modules. But it is still going to be finite. So if we somehow need to be able to serve data that needs more memory capacity, we have to scale horizontally by adding more Memcache instances. In order to take advantage of this additional capacity, the key value space is going to be sharded. The sharding is done so that each of these Memcache instances is responsible for some subset of the key space. And the boundaries, basically from which point of the key range up until which point of the key range are maintained in each of the Memcached instances, these can be adjusted. The shard boundaries can be adjusted, is what we say. Now, remember we had as a design goal to keep Memcache simple. While it is possible to have many different design points, Memcache goes with a design point where the routing decision, the decision to which one of the Memcache instances a request is going to be routed, stays as a responsibility with the client. There is even a so-called MC router component that encapsulates this routing functionality and state. This decision to keep Memcache simple and to offload the routing decisions onto the Memcache clients, as well as the cache fill decisions and some of the other mechanisms that sit with the client, this is what ultimately helps us scale the Memcache, because these are certain operations that now don't have to be executed by the Memcache servers themselves. A single Memcache cluster will also have some bottlenecks. From the client perspective, one limitation is how many Memcache instances it can route across efficiently, for instance. From the perspective of an individual shard that holds hot content, for instance, there may be a bottleneck on the number of requests that can be served for that hot content. Given that the content is just sharded, this means that all of those requests have to be served from the single instance. Also, the more components there are, the more likely it is that there will be some sort of failure on one of the Memcached instances. If that happens, that may have implications on the entire cluster. So instead of having one huge Memcache cluster, it makes sense to organize the Memcache instances into multiple separate Memcache clusters. Each of these clusters will have a smaller number of Memcached instances. In the aggregate, as a solution, this can scale to more requests. It can handle more requests to hot content from the cache, because hot content in this scenario can be present in different Memcache instances on different clusters. The scenario will also have multiple failure domains. So if a failure occurs on one of the Memcache instances, it will impact only one of these clusters, but not the others. The way this system behaves is like having many caches, and a single data item can appear in one or more of them. So now we have a problem because we have multiple copies of the data in the different caches and not just in the database and an individual Memcache instance. To make sure that we maintain content consistent, Memcache uses an invalidation-based mechanism where invalidations are triggered when data gets modified in the database. Although Memcache tried to avoid this kind of solution when it had a single cluster instance, if you remember in that case, it was really up to the client to make sure that the item in the Memcache instance is marked as deleted or it gets updated via the set messages. Now, when we're working with the multiple Memcache clusters, then it becomes necessary for somehow invalidations to be centralized in order to ensure ordering guarantees across all of the clusters. Invalidations are pushed to the appropriate Memcache instances in an order that corresponds to the database commit order. In that sense, it is possible for the Memcache data to be stale, but the updates will not be reordered. Also, the storage tier isn't necessarily a single storage instance as shown in this figure. It itself can be a cluster with many nodes. The paper describes several additional optimizations. Services like Facebook distribute their data and services geographically across many sites. This means that there are multiple Memcache cluster groups at very different locations. The network among these locations will have very long latency compared to what we see in a data center. So it's not realistic to expect that a single sharded cluster will collect the updates from all locations, will respond to cache misses to Memcache servers in each of the locations, and will drive invalidations. Instead, what's done at Memcache is that it expects that at the storage layer, data will be replicated at each of these geo-distributed locations. Now, this other layer of replication can add some additional problems since it creates yet more copies of the data. Memcache addresses this by specifying a protocol on the operations that need to take place when a write is performed in a scenario where we have geographically distributed data centers and then a database that's replicated across those geographically distributed data centers. This line here is the boundary among those geo-distributed data centers. One important thing to note is that we will distinguish among a master database site and the replica databases. When a client web server wants to perform an update, it is first going to set a marker in the local Memcache with the entry that's associated with the value that it wants to update. This marker is going to tell the Memcache that the value is involved in some remote operation, and we need this in case there are some other concurrent operations that will be issued for this value so that we can ensure proper ordering. Then the actual write is going to be performed against the master, the remote master database, and at that point the local Memcache isn't updated, instead its value is deleted. This is because at that time the local database may not have the new value, so we cannot somehow push it in the cache just yet. At some point, the replication logic for this geo-distributed database will kick in, and it will replicate the update to all the replicas, including this one. When the database is safely updated, the marker indicating that this value is involved in a remote operation will be deleted. And you should note that until the marker is deleted, until this operation is completed, the value of this entry exists and can be served only from the remote master database. Of course, one thing that we will want to do is to reduce that cross-data center traffic. Let's now talk about another consistency model called Causal Plus that can hopefully help with this. We looked at a couple of examples which all led to some undesirable scenarios of how data from these large-scale geo-distributed systems ends up showing up in some out-of-order way and confusing the end users, the clients. There are several reasons why if we just use causal consistency models at the system level, it is not possible for us to eliminate these problems and they will keep creeping up. For instance, for causal consistency, the system observes the data accesses in order to determine causality. But when updating the friends list and the postings about the job, these access different servers and therefore they appear as if they are concurrent operations. So it's hard for the system to tell on its own what is it supposed to do, how is it supposed to order these operations. To address this, Wyatt Lloyd, who is now at Princeton, and his co-authors, who were really co-advisors at the time, introduced a new model called Causal Plus, and they presented it in a paper called Don't Settle for Eventual, Scalable Causal Consistency for Wide Area Storage with CUPS. They presented it at the SOSP conference in 2011. CUPS targets a system such as the system we described in the Memcache discussion. Here, in one data center, there is key value-based object store, and here the individual servers, they're denoted with these blue circles. Each of them hosts a portion of the key space, a shard, just like in the Memcache case. The data store is geographically distributed to other locations also, so when a client interacts with this local object store, any of its updates need to be replicated to all of the other locations. In the COP solution, when the client tries to read data, it performs a get operation, and this one is served from the local data store, just like in Memcache. However, one important difference is that the client library is going to capture information about the fact that this data was read. Now, later on, when the client needs to perform a put operation, it's not just going to include the put operation and the value that it needs to update, the key value pair that it wants to update, but it's going to include some ordering metadata. This is not what happens in kind of traditional key value store model. So although from the perspective of the client application, this put may look similar, the actual client library in the COPS model is going to issue a put after operation that is going to provide all the metadata about the dependencies that this put operation has with other values that may have been read previously by this client. The local key value store is going to log this data, and it can communicate this information during replication. When an update gets replicated, the information that's going to be received by the remote nodes is going to include the information about the key that needs to be updated, along with any of the dependencies. And these dependencies are going to have information about the other keys, the other objects in the database that this update depends on, and some information about their timestamp, about their version. This way, the remote object store can now perform dependency checks, and it will not allow this update of KV to become visible here until the dependencies have been satisfied, until dependencies become visible. In this manner, this system ensures a slightly different model for consistency tracking, and this is what's called Causal Plus, which is the new consistency model proposed in this paper. There is follow-on work from the same group of authors that continues to refine new consistency models that allow us to essentially build more useful application experiences from the client's perspective, while also achieving better performance, including in this very large scale and widely distributed data stores. In summary, in this lesson, we talked about some practical aspects of implementing consistency. We summarized few consistency models and the trade-offs they introduce. We talked about different techniques that provide system-level support for realizing a given consistency model. And we used Memcache as an example of a system which was used at Facebook, and this gave us an example to illustrate how these types of techniques can be used to build a real solution. We also mentioned some other more recent ideas on new consistency models, which are useful for globally distributed services that operate at large scales.